Hello, welcome to CADEM CNC Gyan online. This talk is part of a series of lectures on CNC machining from CADEM Technologies. You may be a teacher in a technical institution, you may be in industry, on the shop floor, you may be an entrepreneur. Whatever your role, these lectures are designed to quickly give you basic knowledge of CNC machining, which you can then build upon. This set of 8 videos simplify the complex area of CNC technology. These lecture videos extensively use CADEM's multimedia CNC education software to bring the shop floor live on your screen. Happy learning. In this lecture, I will be talking about cutting tools used on CNC lathes and the importance of selecting the correct tools and tool materials. Hardness, toughness, and wear resistance are the most important qualities of cutting tool materials. The harder a material is, the better it is able to cut another material. Toughness is the ability to withstand shock loads and interrupted cuts. Wear resistance is the ability to retain the shape of the cutting edge for a long period of time. Here is an example of facing where the tool must have high toughness. This part has a number of sharp edges, and each time that the tool comes in contact with an edge, there is a shock load. In each rotation of the part, the tool gets hit 4 times. This is a finished turning operation with no interrupted cuts. The tool does not require high toughness but needs high hardness and wear resistance, so that it can retain its cutting edge for a long time and produce parts accurately within tolerance. This is what common cutting tool materials look like. HSS is the softest material, and at the other end are CBN or cubic boron nitride and PCD, polycrystalline diamond. In this list, HSS is also the toughest material, while PCD is the least tough and most brittle. HSS is used for cutting soft materials like aluminum and for making taps and small diameter drills and reamers. Tungsten carbide, commonly called carbide, is the most popular material because it is hard but relatively inexpensive and is used to cut a wide variety of workpiece materials. Inserts are made by combining hard tungsten carbide particles with a soft binder material, which is cobalt. You can achieve different grades of carbide by varying the proportions of the tungsten carbide and binder. Want more hardness? Increase the amount of tungsten carbide and reduce the binder. Want more toughness? Reduce the amount of tungsten carbide and increase the binder. To increase wear resistance, the insert is coated with a thin layer of harder material like titanium nitride. The thickness of the coating is typically less than 10 microns. By the way, the various colors on inserts are because of the coating. Plain tungsten carbide is light gray, titanium nitride is gold, aluminum oxide is dark gray. A cermet insert, like a carbide insert, is a combination of hard particles and binder. The hard particles are materials like titanium carbide and titanium nitride, and the binder is cobalt. The name cermet is a combination of ceramic plus metal, combining the hardness of ceramic and the toughness of a metal. Cermet inserts are harder than tungsten carbide inserts, but not as tough as them. They have a property that reduces the formation of built-up edge. Ceramic inserts are made of aluminum oxide or silicon nitride. They are extremely hard, have high wear resistance, and can do hard part turning, which is cutting hard materials at high speeds, like hardened steel with more than 50 HRC hardness. They are, however, extremely brittle and cannot withstand interrupted cutting. By the way, aluminum oxide is found naturally as the precious stones rubies and sapphires. This video shows turning with a ceramic insert. you'll notice that there is no interrupted cutting here, and you can see the color at the cutting edge shows the high temperature. CBN, or cubic boron nitride, is the second hardest known material after diamond. CBN is extremely hard, has high wear resistance, and is very good for hard part turning. The whole insert is not made of CBN, but a small bit of CBN is fixed to the tip of a carbide body. This is to combine the hardness of CBN with the toughness of carbide, and also because CBN is very expensive. A CBN insert costs 5 times as much as a carbide insert, but is much cheaper in the long run when thousands of parts are machined. CBN inserts are very popular in mass production, like in the automobile industry. Diamond is the hardest known material. The diamond used in cutting tools is manufactured industrially, not the naturally occurring type. It is called PCD for polycrystalline diamond. It is not as brittle as natural diamond. PCD is very popular in cutting aluminum and copper alloys like brass and bronze at high speeds, like in the automobile industry. The whole insert is not made of PCD, but a small bit of PCD is fixed to the tip of a carbide body. This is to combine the hardness of PCD with the toughness of carbide, and also PCD is very expensive. A PCD insert costs 10 times as much as a carbide insert, but is much cheaper in the long run when thousands of parts are machined. PCD cannot be used to cut steel and cast iron because at high temperatures, in the presence of iron or nickel, which is a common alloying element in steel, it gets converted to its soft form of graphite and becomes useless as a cutting material. This chart shows the application of various cutting tool materials. The x-axis is the toughness and the y-axis is the hardness. As the feed rate increases, you need higher toughness. So you need to use materials that are to the right on the x-axis, like carbide. As the cutting speed increases, you need more hardness. So you need materials that are further up on the y-axis, like cermet or ceramic. Tools can be either solid or with indexable inserts. In an insert type tool, the body is made of steel while the cutting tip is made of a hard material. The insert usually has multiple cutting edges, and when one edge wears out, you rotate or index the insert so that a new edge becomes active. In a turning tool, the insert can be clamped to the holder in different ways. Each method has its advantages and is used for different applications. This video shows top clamping. This is one method of clamping the insert in an external grooving tool. There are different insert shapes and clamping methods for different applications, for making shallow grooves, for regular grooves, for deep grooves, and for parting off. This is what internal grooving tools look like. These tools are for face grooving. Any face grooving tool has a certain groove diameter range that it can work at, a minimum and maximum diameter. A typical grooving insert has these dimensions. This insert has 2 cutting edges, but some inserts may have just 1 edge, and some triangular inserts may have 3 edges. In a threading tool, the insert must have the shape of the thread to be cut. A metric thread insert has a 60-degree tip with the necessary dimensions. A BSW insert will only cut BSW threads, and so on. There are also different inserts based on the thread dimension. The threading insert must always be mounted at the helix angle of the thread so that the insert is perpendicular to the thread groove. Threading holders come with little pieces called anvils that you put under the insert to change its angle. You insert an anvil based on the helix angle of the thread that you want to cut. These are holders for external and internal threading. Inserts can be either partial or full profile types. A partial profile insert only cuts the root of the thread, while a full profile insert cuts both the root and the crest. A partial profile insert can be used to cut threads for a range of pitches, but a full profile insert can only be used for a single pitch. Drills can be solid or insert type. They can also be coolant through drills with a hole through the body through which coolant flows directly to the cutting edge. Coolant through drills are used for drilling deep holes where the normal external coolant does not reach. They require the machine to have a coolant through capability. These are the key dimensions of a drill. The hand of a tool is very important, and selection of the correct hand can be quite confusing. Selecting the wrong hand can lead to accidents and damage to the part, the cutting tool, or the machine. Both internal and external tools come in right and left hands for turning, grooving, threading, and boring. The hand of the tool to be used is decided by the turret position and whether the tool is mounted face up or face down. For example, when you want to cut towards the chuck with the tool mounted face up, you would use a left hand tool on the rear turret and a right hand tool on the front turret. An insert is usually made of not just one material but is a combination of different materials. So the word grade is used instead of the word material. The cutting edge geometry and the grade of an insert are equally important when selecting an insert. The correct selection of cutting tools and cutting parameters, which is cutting speed, feed rate, and depth of cut, is the key to achieving high productivity in CNC machining. Which cutting edge would you use to cut a tomato? The axe or the kitchen knife? This picture shows the cross sections of an axe and a knife. The axe has a broad, strong cutting edge that can withstand high cutting forces, and the knife has a narrow, weak cutting edge that cannot take high cutting forces. Neither cutting edge is better. Each has a different use, and if you select the wrong cutting edge for an application, this is what happens. The knife breaks if you try to cut wood with it, because it cannot withstand the cutting force. If you try to cut a tomato with an axe, the tomato gets squashed instead of being cut. The cutting edge geometry is as important on the shop floor as it is in the kitchen. The logic of selecting the cutting edge too is the same. Inserts have different cutting edge geometries for different materials like steel, stainless steel, cast iron, and aluminum. There are also different geometries for different applications: roughing, medium machining. The first insert at the top in this picture is for roughing of steel and cast iron. You can see that it has a blunt cutting edge with a flat land of 0.32 mm. This is because roughing involves high cutting forces and may have shock loads because of interrupted cutting due to the part geometry itself, or because of blowholes and sand inclusions in castings. This is like the axe cutting wood. Medium machining involves a smaller depth of cut and feed rate and smaller cutting forces. The insert for medium machining, the one in the middle, therefore has a smaller land of just 0.21 mm. In roughing and medium machining, the cutting forces also cause distortion and bending of the part. The dimensional accuracy is poor because of this, but we are not bothered about accuracy in these operations. The aim is to remove material at a high rate. In finishing, there are no shock loads because there is no interrupted cutting, and the cutting forces are low because the depth of cut and feed rate are low. The cutting edge in this case, therefore, is sharp with zero land. The sharp edge also results in low distortion and bending of the part, which is required for getting close tolerances. This is like the kitchen knife for cutting a tomato. Based on the angle at which the insert is held in the holder, you have two types of inserts, positive and negative. Every insert must have a relief angle when it is cutting the part, so that only the top of the cutting edge is cutting and the side is not cutting or rubbing. The positive insert has a net positive rake, which means it slopes downwards from the tip. The positive insert has a relief angle of up to 20 degrees. Because of the relief angle, the insert can be held flat in the holder. Also, because of the relief angle, you get a sharper edge that results in lower cutting forces. Lower cutting forces mean less part distortion and better dimensional accuracy. So positive inserts are used to cut slender parts or parts that have thin walls. Because of the sharper edge, they are also weaker and cannot take heavy cutting forces. All these are positive inserts. You can clearly see a positive rake angle at the top and the relief angle at the side of the insert. This is a negative insert. It has a net negative rake, which means it slopes upwards from the tip. It does not have a relief angle on the side, and the side is perpendicular to the top. Since it has no relief angle, a relief angle must be created by holding the insert at an angle in the holder. Also, because there is no relief angle, you get a more blunt edge with a high cross section, stronger, that can withstand higher cutting forces. Because of the more blunt edge, you also have higher cutting forces that result in more part distortion and bending. All these are negative inserts. You can clearly see that there is no relief angle at the side of the insert, and the side is perpendicular to the top. This video shows a negative insert cutting a part with a square cross section. Each time that an edge hits the insert, there is a heavy shock load, and this happens 4 times in every revolution. The insert has to withstand all this. A shoe must be comfortable on the feet, made of material that is soft and that molds itself to the shape of the foot. Leather has this quality, so we make shoes out of leather. But this same quality of softness causes problems on the sole, which wears out fast. We want the body of the shoe to be soft, but the sole to be hard. So, to get a hard sole that withstands wear and tear and has a long life, we stick a sheet of hard rubber on the sole. We are combining the comfort of the leather with the long life of the hard rubber. We have a similar problem with inserts, and a similar solution is used. We want a cutting edge to be hard so that it can cut faster and have a longer life. Unfortunately, the harder a cutting tool material is, the more brittle it is and the easier it breaks. We need two opposite qualities, toughness and hardness. We want the body of the insert to be tough, but the cutting edge surface to be hard, with high wear resistance. To improve the wear resistance and life of an insert, we just coat it with hard but brittle materials like aluminum oxide, titanium nitride or titanium carbonitride. This picture shows a plain tungsten carbide insert, the grey one on top, and a coated insert, the gold one at the bottom. An insert may have multiple coatings of different materials. The cross section shows 3 different coatings, each between 2 microns and 10 microns thick in this picture. Cutting tool manufacturers make inserts with different grades and chip breaker geometries for different workpiece materials and applications. So please remember this picture, and remember that you cannot just take any available insert and start cutting. If you want to reduce cycle time, get good quality parts, and make money in CNC machining, select the correct grade and chip breaker geometry from the catalogs of cutting tool manufacturers. This is the convention for turning tool holders. The name defines the size, style, and hand of the holder, the size and shape of the insert, and how the insert is clamped to the holder. The picture below shows the names of some holders with various insert shapes and clamping types. The full name of a holder is like the one shown on top, PSKNR 2525 M12. The first and second alphabet of the name are the clamping method and insert shape. For example, if the holder is for a square insert, the second alphabet of its name will be S. The third and fourth alphabet are the holder style and the insert clearance angle. For example, if the clearance angle is 5 degrees, the fourth alphabet will be B. The fifth alphabet is the hand of the tool, and the 4 numbers after that define the shank height and width. The height is the first 2 digits and the width the next 2 digits. For example, 3225 would mean a height of 32 mm and a width of 25 mm. This is the length of the holder. Each alphabet represents a specific length, like M means 150 mm. This is the cutting edge length of the insert. The number 12 would mean a cutting edge length of 12 mm. This is the convention for boring holders. It is almost the same as for turning holders, except for a couple of differences. The first alphabet indicates the type of bar. The number after that is the bar diameter, and the alphabet after the number is the bar length. Inserts have a naming convention too that defines their shape and size. The first 2 alphabets are the shape and clearance angle. The third alphabet is the tolerance to which the insert is manufactured. The fourth alphabet is the type of clamping. The fifth parameter, which is a 2-digit number, is the cutting edge length of the insert. The sixth and seventh parameters are the insert thickness and the nose radius, both 2-digit numbers. These are the key messages from this lecture. These are the key messages from this lecture. I hope you found this talk useful. If you have any questions about CNC machining, please call me on the CNC Gyan helpline.